This video is an introduction to creating peak models and how they apply to XPS data. And during the course of this video, we should provide answers to questions such as these. Why create a peak model in the first place? How does one create a peak model? What is a component? And do I need to use constraints when fitting a peak model to data? The first question is, why do we need peak models? And this is an example where a peak model is an essential part of understanding the material properties. This is a sample that contains aluminium and copper, and because it has been measured using an aluminium K-alpha X-ray source, which is very common for most lab-based systems, the aluminium signal arrives only in the form of aluminium 2s and aluminium 2p, and the problem is that copper 3s and copper 3p overlap with the aluminium signal, and then on top of this there may be different oxidation states of aluminium or even different oxidation states of copper, and in order to separate different oxidation states, then a peak model, as can be seen here, is an essential part of analysing XPS data. So what do we mean by a peak model for XPS data? Well, a peak model is defined by a list of component curves representing photoemission plus curves that represent inelastically scattered background signal. So in some sense, to describe this as a peak model is not entirely accurate, because some of the curves are not peaks, they are not bell-shaped curves. A peak model is a collection of line shapes, bell-shaped or otherwise, the otherwise meaning background curves. And then a peak model should be capable of adjustment to allow a synthetic envelope to reproduce the spectroscopic data. Now this is an important part of a peak model, is that we must be able to recreate the spectrum using the components and optimization, and the peak model should fit the data with a precision consistent with the uncertainty in the data. Now most importantly, it must be open to physical interpretation, so the peaks have meaning, and we'd like to assign different chemical state or different elements to different peaks within the peak model. So the peaks and the background must be such that we can separate the signal from these distinct sources. This includes chemical state and background signal. And then at the end of the day, we must be able to use the information from the peak model to quantify a sample in terms of chemistry or other physical properties. A component is part of a peak model. Here's an example of a peak model where there are three components, and the characteristics of components are that they are defined in terms of a line shape, which specifies the type of curve that will be used to fit data. There's an area parameter, a full width half maximum, and a position. And the idea of fitting a component to data, which is an isolated peak in this instance, is that we can identify the position of the peak. This represents a measure for the binding energy that's associated with a photoemission process, the area of a peak, which represents the intensity of the peak, and the full width half maximum that relates to both physical properties of the peak and also the resolution with which the instrument is measuring the peak. So the full width half maximum is not quite the same as the area and the position. Both the area and the position ought to relate to physical properties that we can associate with the material properties of a sample. For a particular set of data, a peak model is just a list of these components. So we can see here we've got a silver 4s, and it is defined using one of these columns on the components property page, and it includes a line shape, the area, the full width half maximum, and the position as before. However, it's now associated with a set of other components that are all defined on these data, and taken as a group, when optimized, the parameters are all adjusted so that we end up with an envelope that fits these data. This is an example of a peak model that involves 4 components and a background curve. However, only 4 components are included as part of the optimization, because in this case the background is calculated directly from the data. It happens to be a very simple background. It's just a minimum limits background that turns out to be horizontal. And this is a characteristic of the material that we're analysing. In this case, there's a large band gap, so we don't expect to see a response in the background shape due to these photo emission peaks that we're trying to measure. Hence, making use of a flat background is appropriate in this instance. But there are other cases where the background can be calculated from the data and it represents some type of response. So, for example, a Shirley background would be applicable to a metallic type material where there's an immediate response to a photo emission peak. TwoGuard background are another form of calculated background that again calculates a curve based on a different algorithm from the Shirley algorithm, but nevertheless there's a similarity in the sense that they both calculate a curve from the data. And a linear background, well, this is very similar to this minimum limits. The only difference is the intensity at either end of a linear background can be different, whereas the minimum limits, they're both the same. So the bell-shaped curves are the only components within the peak model that are optimized to fit these data. A more advanced use of components in a peak model is to introduce components that represent background signal. So here we have a peak model where there are two components that are indicated. That's the AG4P BG and the silver 4S background. Now the silver 4P is modeling signal that derives from the silver 4P peak, which is a higher kinetic energy. And inelastic scattering of these higher energy electrons manifests within these data as a sloping background that is well approximated over this interval by a linear curve. Similarly, we have silver 4S and a background that is a result of an immediate response in the background signal to this silver 4S peak. So we end up with this sigmoid shape beneath the silver 4S peak. And in order to model these data, all of these components are summed together. And these are summed to form this synthetic envelope, which is the approximation to the data. Fitting a set of components to a peak model is only part of the story. What we would like to do, once we've made a peak model that fits these data, we would like to relate these components to some chemistry. And this represents a peak model that could be a result of chemistry of this form. We can explain this peak model in terms of different numbers of carbon atoms that are bonded to other atoms, either carbon, nitrogen or oxygen, and also the type of bond involved. So when we look at this peak model, we find a component with a binding energy that has been assigned 285, and then other peaks are referenced relative to this binding energy, and we would like to interpret these binding energies as being associated with these different chemical bonds. So first of all, we can say that we've got a CH peak. We've got one that is a carbon that is bonded to carbon, but it's bonded to a structure that is more involved than just a simple carbon-carbon. So there's an offset here in binding energy, and then there's another offset for the carbon that are bonded to nitrogen, and we've got two of these. And then we've got a peak here, which is a carbon that is doubly bonded to oxygen and singly bonded to nitrogen. So each one of these different chemical environments for the carbon atom produces a different position in binding energy for these photo emission peaks, which are then measured using the components that are fitted to these data. So the next thing that we need to look at in terms of interpreting the peak model is the relative intensity of these peaks. So we can see here that we've got a 2-to-1 relationship or a 1-to-1 relationship between these peaks. So we've got two here that are twice the size of these two here. And is this consistent with this chemistry? And the answer is yes, because we can identify two carbon atoms in this chemistry that are essentially CH in nature, so these would contribute to this component. And there are two that are bonded to nitrogen and bonded to carbon. So again, 2 would suggest these two should be the same intensity and therefore the same area. And then we've got 1 double bonded to oxygen, and we've got 1 that is in this state where it's bonded to carbon and carbon, but this carbon has some complexity in the bonding, therefore it's offset slightly. So we've got 2 that are half the size of the other 2, and this is consistent with the chemistry we see here. So this is an example of how one might interpret a peak model in the context of chemistry. When optimization is performed, a given peak model fits data with a given precision, but this is not the final target for the peak model. It isn't simply to reproduce the data. This could be achieved by other means that do not involve bell-shaped curves or curves that represent the background. The idea is that we identify signal that originates from different sources, measure the amount of substance, measure the position, and use it to understand the sample. So when we create a peak model, we must have components that are physically meaningful. For example, here we have 2 doublet peaks. These doublet peaks derive from the physics of the photoionization process, where platinum in a 4F state, when excited by a photon, has 2 final states that are close in energy and are related by physics. They ought to be in a given ratio for a given photon energy. So the model that we fit to the data must provide a ratio of peaks that is consistent with physics. And we must have shapes for these peaks that allow us to separate signal from background and to measure the amount of signal for each one of these peaks. These are all important parts of a peak model, and they are dependent on line shapes. So to achieve a meaningful fit to data, we must have meaningful line shapes. Line shapes are an important part of a peak model. They represent a constraint on how a peak model can fit data. Traditionally, 2 functional forms have been used to create line shapes that are referred to as synthetic line shapes, that is, to imply that they are mathematical in origin and not deriving from data as such. So to fit data, the line shapes that have traditionally been used are these pseudo-Voigt line shapes that are typically referred to as GL or SGL line shapes. And these are both constructed from a Lorentzian, which has a shape that is characteristic of a photoemission peak, and a Gaussian, which is intended to have a shape that allows a modification of a Lorentzian based on instrumental factors or other factors that are altering the shape of a photoemission peak from the expected Lorentzian shape. And this is to do with the measurement process. So a pseudo-Voigt function is a form that is constructed as a GL as a function of x and a parameter m that represents a product of a Lorentzian with a Gaussian, and the difference between the values for m are that the full width half maximum of the Lorentzian and the full width half maximum of the Gaussian are related by this m parameter in these terms. There's an alternative to the GL line shape, is the SGL line shape, and this is again a combination of a Lorentzian and a Gaussian. The Lorentzian and the Gaussian have the same full width half maximum, but what differs is the relative intensity of the Lorentzian and the Gaussian, and they're summed to form the line shape that results from these 2 functional forms. And these are very useful in the sense that they're computationally efficient. We can calculate a new line shape very quickly by means of these 2 functional forms and combining them in these ways. Now, in reality, the line shapes that are produced by experimental measurement of photoemission peaks tend to be different from these pseudo-Voigt functions, and historically they have also been modeled by a true Voigt-based line shape. and that is to say a line shape that is not simply a product or a sum of these Lorentzian and Gaussian line shapes. It's a convolution of a Lorentzian with a Gaussian of differing width, and it produces a different sequence of curves for a given mixing parameter. The mathematics of these line shapes is not necessarily as important as the shapes themselves. If we look at the relationship between a Lorentzian and a Gaussian, you can see the Lorentzian has extended wings, and we often see this shape in photoemission lines, especially s orbitals. These produce Lorentzian-like peaks, and it's important to have a line shape that can accommodate Lorentzian peaks. On the other hand, the Gaussian peak is much more compact, and you can see the wings are not there, and this would be more characteristic of photoemission peaks that are measured with an instrument where the energy resolution is not quite so good and you've got blurring of information. So having Gaussian character is also important. And this is the motivation for producing these two computationally efficient line shapes, the GL and the SGL. But if we look closely, you can see that the parameters that we choose for these GL and the SGL are not equivalent. You can see that GL100 is a Lorentzian and GL0 is a Gaussian, and the same is true for the SGL 100 and 0, but they don't move smoothly between a Gaussian shape and a Lorentzian in the same way. So there is a difference, first of all, to note between these two shapes. And then secondly, there's the Voigt function, which they both try to approximate, and the smoothness of movement between the Lorentzian shape and the Gaussian shape is much better, and it does something else. It tends to produce some Lorentzian type curve even for the more Gaussian shape. So this is a better way of approximating peaks that are essentially Lorentzian. The curves we use for backgrounds tend to be more limited in number, but nevertheless are quite complex in their calculation for a given set of data. And they do have an influence on the shapes that we see in data that we need to fit with the bell-shaped curves. That is, if you take any one of these three backgrounds that we see here and we subtract them from the data, we end up with a slightly different shape for the photoemission curve, and this is an important part of fitting data by curves. So since these are the three most commonly used background types, that's a linear, Shirley and a TwoGuard background, it's worth having a look at these and how these different shapes arise. So if we look at a TwoGuard background calculation, this is based on an integral of this form, where a cross-section, which has a functional form that we see here, is convoluted with the data using an integral from e to infinity to produce a background value at each energy which responds to the photoemission signal in the peak. So in this instance we've got a silicon dioxide TwoGuard background. These values B, C, D and T0 are calculated by TwoGuard for this particular material, and when we apply this background to these data, which are from silicon dioxide, then we end up with a shape that matches the background, the inelastically scattered background, very well. And one should observe here how there's a flat response beneath the peak, and this is part of the design of these parameters that are applied to the cross-section, which are then fold into the spectrum to calculate this background. The alternative that is often used to a TwoGuard background is a Shirley background, and the Shirley background is calculated in an iterative scheme because we need to calculate from data the areas A1 and A2 and then combine these areas together with these intensities I1 and I2 to calculate a background at a given energy. And since you don't know the background, you can't calculate these areas, therefore you must iterate in order to calculate the shape that we see here. Now, as an alternative to using the data to calculate a Shirley background, we can use a line shape and calculate the response that is equivalent to this calculation directly using an integral, and this integral produces a shape. But what we don't have when we specify a background that is calculated from a line shape, we don't have this increase in the background from the start to the end of the interval of which a background should apply. So that leaves a parameter that needs to be fit as part of any peak model that might use a line shape and a component that has a shape of a Shirley background. So this is an example of where an active background component is used as part of the peak fitting. Once a peak model has been established for a set of data and we fit the peak model to the data, the question is, how do we measure the goodness of fit for these data? And the two metrics that are available are the residual standard deviation and a root mean square. And the difference between these two metrics has an influence on how the residual appears, and it also, if we choose these different metrics for the figure of merit when optimization is performed, alters the way the data and the peaks relate to one another. And the reason that there is a difference between these two figures of merit is when we have a root mean square figure of merit, then the shapes we see here in the residual plot are reflected in the optimization steps. That is, that there is no normalization of the differences between the data and the synthetic envelope that take account of variation of noise within a spectrum. Now, the noise in a spectrum for pulse counted data should be proportional to the square root of the counts per bin. And you can see the square root of the counts per bin enters into the residual standard deviation calculation, or the chi-square calculation. And without normalization, the noise level within the data increases as the intensity increases. Therefore, around a peak maximum, you have greater oscillations when you are working with a root mean square. And this means that when you optimize, you're going to fit with greater emphasis the peak model to the data around peak maxima. And this is in contrast to the residual standard deviation, where normalization is performed, and when the residual is normalized to reflect what happens when you have a residual standard deviation or a chi-square figure of merit, then the residual has this uniform appearance when you have a good fit, that is. And this is an indication that this curve that fits the data is fitting the data equally across the entire energy range. So the maximum and the background is fitted with the same weight. So a residual standard deviation or a chi-square tends to fit the data evenly across the entire interval, whereas in the case of a root mean square, the emphasis is placed at the peak maximum. The term least squares derives from the figure of merit calculation. Both the chi-square and the root mean square both involve the difference between a data envelope and a synthetic envelope, and that value is squared, and then we sum to produce a single figure of merit. So the question that we should ask ourselves is it possible to fit data with a set of curves purely based on a least squares criterion? And the answer is yes, you can, but under certain circumstances. If we consider this example here, then what we have is a curve which represents the target spectrum and a least squares spectrum, and these are marked by a cross and a plus, and then a set of 4 component spectra. And when these component spectra are fitted to these data, then the overlay of the crosses and the pluses produces a star, indicating this is an outstandingly good fit of these 4 components to this target spectrum. But this should not be surprising, because the way these data have been constructed is that the target spectrum is a set of components that have been scaled and summed, and so we have provided the ideal situation where the target spectrum is entirely constructed from the components that the least squares criterion is trying to fit. So it is possible under ideal conditions to use a least squares criterion to fit data. with components. When we try to use nonlinear least squares fitting of data, the scenario changes. We do not have typically line shapes that are perfectly the shape of the photoemission peaks. So when we perform a peak fit, we obtain a residual standard deviation and a residual plot that is only an approximation, and we have to accept that it is not necessarily going to be perfect. Now we have a situation here where these are data that have been constructed, so we know the number of components, same as in the previous example. There are 4 components. We know the relationship of these components in reality, but we do not have precise synthetic line shapes that match the data for these individual components that were previously fit to the data envelope. However, making use of these components, so I have the shapes for these different components that are used to construct the data envelope. If I calculate by monitoring the chi-square against the line shape parameter, then I can identify a shape that best fits each individual data component. So I can estimate what the line shape ought to be, and we can see here that I've got 2 examples where I've calculated 2 different line shapes for 2 different components that are included in this peak model. So now there are 4 components with 4 line shapes, and when these components are fit to these data, we end up with a ratio for these components, and we end up with a residual standard deviation. And we can see here that it's not ideal. In no sense is this the residual standard deviation that you would expect, and the residual itself is not uniform. Nevertheless, given that we do not have the perfect line shapes for these data, we sometimes have to accept that we do not have a perfect residual and a perfect residual plot. If the line shapes were the precise line shapes for these data, then it might be possible to use nonlinear least squares to fit these data and produce the correct ratio for all of these peaks, and the offsets also agreeing with the construction of this spectrum envelope. If we don't have the ideal line shapes, then we have to lend a hand to the optimization process by introducing some constraints. And here we have an example of a peak model that is applied to these data, where constraints have been introduced in such a way that we return the value that we'd expect for the offset between these peaks and also the ratio of these peaks. These peaks were designed to be offset by increments of 0.5, and the ratio of these peaks should be 1, 1, 2, 4. So introducing these parameter constraints that are constraints between the full width half maximum and also the area between 2 peaks, and then we've got another pair of constraints here that relate another pair of these peaks, and with these constraints we end up with the expected return from fitting this peak model to data. And this is important because these ratios and these offsets are what determines our interpretation of chemical state and structure of a chemical compound. Now we can contrast this by looking at the same peak model fit without the use of these constraints. So when we look at this new form of the peak model, where you can see now the constraints are simply interval constraints and there's no relationship between offsets, full width half maxima or area, then we end up with a superior residual standard deviation, a more uniform residual plot, but the ratio of the component peaks is no longer the same. We've now got something that looks more like this larger peak is 5 times the intensity of these smaller peaks, and this would be misleading if we're trying to understand the chemistry of a sample. So the importance of constraints of this form can be seen that we must return intensity ratios and also offsets in binding energy that will match our understanding of the chemistry, and this is only possible if we have line shapes that don't fully match the true line shapes if we introduce these constraints. To further illustrate the importance of constraints, the example here is making use of the full width half maximum constraint between a set of component peaks. These data are once again constructed, and they're constructed to have peaks in the proportions 1 to 5 to 2, and there should be an offset between these peaks 3 and 6 eV, so 0, 6 and 3 eV. The components themselves are designed with line shapes. These top two are Voigt functions that have been optimized based on the individual data that were used to construct these spectral shapes. So these ought to be really quite good approximations to the line shapes, at least the best we can do in terms of a synthetic line shape of this form. The bottom pair are peak models that are using a line shape that is less than optimal for these particular data. And by using less than optimal line shapes, the fit in terms of the residual standard deviation has been achieved by adjusting the limits for the interval over which data are fit. So we can see here we've got two different residual standard deviations, the same interval, the same line shapes, but the difference again is that the full width half maximum is constrained in the one case, whereas it's allowed to vary in the other case. So when we look at these results, we can see that if we've got a good line shape and we fit the data without any constraints, we end up with a set of offsets that don't quite match the outcome that we would like. So it ought to be 0, 6, 3, not quite, it's close but not quite. Similarly, the area ought to be in the ratio 1, 5, 2. It's close but not quite. But once we introduce the constraint of the full width half maximum for all peaks are identical, then the result is really quite good. We've ended up with an offset of 0, 6, 3, and that is the expected, and the ratio is 1, 2, 5. It's very close. On the other hand, when we look at a line shape that doesn't approximate the data so well, we end up with offsets that are not dissimilar from the unconstrained peak fit using a line shape that is more appropriate. However, the area ratio, this is very different. We've got 4 instead of 5 for the area of the most intense peak relative to the least intense peak. So this is producing an erroneous result in terms of the structure of these peaks. When we constrain the less than appropriate peak model using the full width half maximum, then the outcome, well, again we get very good offset results. The ratio of the areas has improved over the unconstrained form, but it's not nearly as good as when we have good line shapes and meaningful constraints in terms of full width half maximum. So the full width half maximum and having a good line shape is an important part of getting good results out of fitting data with components. From these examples we can conclude that peak fitting and peak models are an important part of interpreting XPS data. They are an essential part of it. However, the line shapes that we use in these peak models must be as close as possible to the line shapes that are generated by the photoemission process and the measurement process. This is very important to getting good scientific results out of your peak models. And in the absence of the ideal line shapes for a particular set of data, then we must introduce some parameter constraints to guide optimization to a realistic, physically meaningful outcome. The examples of spectra used throughout this video were calculated from a spectrum that was measured from a silicon dioxide sample, and it's the silicon 2s spectrum. It has one peak and it has a background response. So this particular spectrum has been shifted and then combined in various multiples to produce different envelopes that could be used to understand how peak fitting and data relate. So these are all examples of spectra that were used as part of this analysis, and this is an example of the data file that was used and constructed to make these different data envelopes, and these are the spectral shapes and hence how the line shapes could be determined that would fit these data.